Good morning. Welcome to Questacon. I'm Graham Durant. I'm the director here. It's my pleasure to welcome you all here, particularly you guys from Namaji School. Thank you for coming in today. You're going to have a really exciting talk. It made me think, when I was a teenager, 50 years ago, I was watching this little grainy black and white television of man's first step onto the moon. Your generation are going to watch not only men and women going back to the moon, but you're going to watch the first people stepping foot on Mars. That's my prediction. So when you're my age, you'll be able to look back and say, yep, I remember when mankind first stepped onto the surface of Mars. So how exciting is that? Space is really fascinating, and we're lucky in Australia that there's now such a focus on space, particularly with the founding of a new Australian space agency. And it's my pleasure to welcome the CEO of that space agency to say a few words, Dr. Megan Clark.
Thanks, Graham, and thank you all for being here. I'm also here not really to introduce Badri, although I will do that, but I'm actually here as a student to learn from Badri today. So I'm joining this audience exactly the same reason that you are here. You are truly honoured to be able to hear from Dr. Badri Younes. He's the Deputy Associate Administrator and Program Manager for NASA's Space Communication and Navigation. What that means is he looks after all aspects of communication at NASA, between the Earth, in space, what's happening in space, in deep space. So you are truly hearing from an expert, and I don't want to stand between that and your learning. So Badri, my good friend,
yeah.
It is a pleasure to introduce you, and I know you will enthrall this audience.
Thank you, Meg. Thank you very much. I'd like to make a correction. I don't think that you are the generation that you are going to see people landing on Mars. You are the generation that you are going to land on Mars. As I look around, I see future astronauts, scientists, engineers, educators. You know, you guys have the foundation for shaping the future and carrying on with what NASA is doing, with what NASA is all about. And what are we all about? Exploration. I'm so happy, that Australia has finally, set up the Australian Space Agency under the leadership of Dr. Clark. Many of you in the past wonder where to go next. How do you apply your knowledge? How do you shape the future? Now you have something, that provides some focus and a roadmap for all of you. So please, all of you, work with the space agency, look toward the space agency as a mean to apply your capabilities and what you are learning to shape the future. So good to be with you. I'm always so happy to be here down in Australia. I always thought Australia down under is the best place to see the world way up above. And that's why for the past 60 years, we've had this great relationship with Australia. It's a partnership, true partnership. We have it with CSIRO, and we collaborate on space. And CSIRO, as you all know, manages and operates the Deep Space Station here in Tinbimbilla. And I know many of the students in here come from that area, so I hope you all have visited that Deep Space Station. Let me introduce my team in here. I'm not alone, and I'm not the one who's doing things, making things happen at NASA. We have a team. We work in team. Teamwork is essential. The collective power and knowledge of the many is by far better than knowledge and the power of the one. So always work in team. Collaborate together to make things happen. You can get there faster and better. So let me introduce, starting from Sue Chang. She leads our network services. Mr. Marcus Watkins. Barbara Addy, and Susie Dodd, as well as Greg Mann. Why am I introducing these folks? Not to show you their pretty faces, but to tell you and to show you that among them, I have 3 capable women. You know, NASA, you know, is a good place for everyone, and we've demonstrated that women in leadership position can make things happen. Among these 3 ladies, I have this lady, Susie Dodd. She has gone where no one has gone before. She has 2 spacecraft that have gone beyond the solar system into the interstellar areas. That's about 20 billion kilometers away from here. And she's still going. And thanks to her and her technical expertise and management and leadership, we made it over there. And so many of you ladies over here can do the same thing. You have the potential, as well as the guys, to do the same thing, to go where no one has gone before. And we need to do that. But first, let me talk a little bit about myself. This is my name. It's hard to pronounce, you know, and hard to remember. Badri Younes. I'm presently the Deputy Associate Administrator. I have overall responsibility for all space communication and navigation for NASA. What does it mean? I'm responsible to develop, operate, and manage all space communication capabilities. We develop the technology, as well as we take care of the utilization of the radio frequencies, the radio spectrum, because without the spectrum, we cannot do science and we cannot communicate. And we work on making sure that we work the standards such that everyone can talk when machines connect to each other. You know, the flow of information can take place. And we work with international entities, and we represent NASA in these discussions, negotiating on their behalf. We do all of this because we have a lot of responsibilities. On a daily basis, we support more than 100 spacecraft flying either in the near Earth or far away, all the way to the interstellar areas. And we do that 24/7. That means around the clock. You know, we have science missions flying through space, transmitting data. And data coming out of sensors and instruments on board. This is our way of sensing and viewing and understanding the makeup of things or what's happening elsewhere. And this is where our asset located. 3 different networks. They support different missions. You know, in particular, you know, we have the near Earth. These are missions that fly around the globe, studying Earth and connecting back and transmitting their data back through the polar region because they fly around the polar areas. We also have the space network. These are stationed up in space, and they see everything that's happening under them. So when a mission flies around, you know, if the station in here and they cannot transmit the data to their station, they send the data to the satellite, and the satellite sends it back to Earth. And we also have the Deep Space Network. And as you all know, one of these stations is down here in Tinbabilla. I hope you all have visited the place, and if you have not, why not? It's a good place to visit. We have a visitor center that talks about the science we do. We do that in collaboration with the Australian government, in particular CSIRO, and hopefully in the future, similar things we'll be doing with the Australian space agencies. Australia is on its way to carve a place for itself within the space industry. So we have a number of antennas. One of them is so huge, 70-meter wide, and the other smaller size antennas. So please, if you have not visited our place, go there. So why do we do that? Because we are curious by our nature. We are always wondering about what's out there. Are we alone? Are there other planets or human beings or other beings elsewhere? You know, we need to understand where we came from, where we are going. And we study so many things to answer these questions. We explore. Australians, by their very nature, are explorers and pioneers. You have that spirit within you. And this is the kind of spirit that's going to carry, you know, Australia into the future. And not only Australia, mankind altogether. We are really counting on you guys, you know, to go into the future. So let's explore. Can I show the video?
"50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible.
Very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off-planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
and more in testing,
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next-generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface. The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity.
In a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going.
We're going.
We are definitely going. You know, how many of you would like to be an astronaut? Because of the light, I don't see clearly up there, but I hope many of you say, okay, this is good. Being an astronaut is a good thing because you can go to places where no one has been before and really explore in person. But is this the only thing NASA does? No. Much of our exploration is done, using robotic mission other than relying on human. They prepare the way, they pave the way for human to go there. We have spacecraft that go all throughout the heavens to study the planets and beyond and to study the universe, as well as spacecraft that study Earth. So that's what we do. We study Earth. We do heliophysics. Heliophysics is a study of the sun and the heliosphere. We study the planets, and we do astrophysics. We look at the heart of the universe, trying to see whether there are planets or elsewhere, and the origin of the universe. How were we created, and where are we going? So let's begin our journey. Our journey starts with Earth. And why do we study Earth? Why do you think we study Earth? I'm giving you the answer on the slide. Because we would like to understand, how to improve our ability to forecast natural hazards, be that the ones that are naturally made or the things that are man-made. Everything is just to ensure that human beings and their quality of life is preserved or improved. We study Earth because that's the only place we know, where humans exist. We study Earth because we are trying to understand what enables life. Why is it Earth? There are many things that enters into the nature of Earth and its ability to support life. In particular, we have water on the surface. There is something we call a magnetic field, a magnetosphere around the Earth that's protecting it. It's like a bubble protecting the Earth from outside hazards. Our proximity to the sun, we are just about the right distance from the sun. Our atmosphere, it's a very delicate, balancing environment, balanced environment that exists over there. And we are looking at the Earth by itself. It's a highly dynamic Earth. It's a living Earth. It's not like a dead rock, There are things that are happening inside, making the planet real lively, more dynamic, a living planet. And we look at also the organic molecules, the basic element for life to exist. There are a number of components that are associated with Earth. The geosphere, the hydrosphere, the atmosphere, the cryosphere, and the biosphere. But before I get to that, I'd like to talk about the Earth itself, the makeup of the Earth. At the heart of the Earth, inside, we have the core. The core is because, the gravitational forces and because of the spinning of the Earth is under a lot of pressure, and there is the weight of everything on it. So it's extremely hot. It's like about 5,000 to 6,000 degrees Celsius. It's almost as hot as the surface of the sun. But because of all of this pressure on it, it's like solid. Now, as you move to the outer core, is less pressure. And because of the heat, the iron, and also there is nickel there, is like, it's melted, it's fluid. And then you go to, the mantle, and then the outer mantle, and all the way to the crust. You know that the crust, where we live, and the oceans and everything, the mountains that we have, and everything that we know is only probably so thin like the skin of an apple. The rest is the inside that has nothing to do with life as we know it, but is very essential to life. What's happening in here? Because of the heat generated inside, it's like when you are boiling water, the heat comes from the bottom goes up and the cold things go down. There is a convection process taking place. We call it convection current. What's up? Excuse me? Yeah. But, I would welcome questions, but for me, let me finish with the presentation and I can answer all of your questions at the end, okay? And so this convection current and also the spinning of the Earth, this swirling whirlpool, because of the spinning of the Earth, create an electric current that create also a magnetic field. The sum of all of magnetic fields generated inside by this process create a big magnetic bubble around Earth. And that's very essential for life to exist on Earth. And I will get to it later on. The other component of Earth, there's a delicate balance between what's happening in here. Earth, the upper structure of Earth is riding on about 15 plates. We call them tectonic plates that are not stable. They keep on moving. They create mountains. They create valleys. We are talking about the biosphere. Every biological thing that exists, every living things participate in this process, from plants to animals to everything. We are all part of this biosphere. The cryosphere, the amount of snow and ice, is our big reservoir for potable water. And also, the amount of ice on Earth is so critical because what happened, the ice reflects energy, and reflect at least 1/3 of the energy coming from the sun, keeping the temperature in the around Earth, very tolerable. Otherwise, we'll have had much hotter environment. The atmosphere, this balance that exists in the atmosphere, the composition of the atmosphere, if all of these things are so very much interrelated, So the interconnection, all of these things, I can give you a couple of examples. One of them in the water cycle and the other, the carbon cycle. As you all know, the water, what happened in the ocean, whatever, because of the sun, it evaporates, then, the wind and everything moves that around, and then you have condensation, and then you have rainfall. It comes down in the form of snow and so on. It's a continuous process. The same thing with carbon. The carbon cycle is so critical because, the amount of carbon in the air is something that needs to remain at a certain level. Otherwise, the amount of, there will be the kind of temperatures that may impact the quality of life on Earth and probably be detrimental to our presence on Earth. That's why the amount of, the forest, whether it's on the surface or underneath the ocean, are so critical to take in these carbon dioxide from the air and transform it back into oxygen and carbon that can be stored back in the Earth. Anything that we do from, around Earth, the cars that we drive and all of these things do affect that. They produce the kind of things that that are impacting to the environment. So this balance is so critical for life to continue. And how do we study that? The study of Earth, in the past we relied on balloons. Balloons, these are huge balloons. Each balloon, can contain the size of about 100 Goodyear blimp, if you are all familiar with that. So they are so huge. The material is made out of thin nylon, and they fly way up high, like 60,000 feet or about, do the conversion, about 20 kilometers up in the air. And they drift, and we study the weather, and we study, many things around the Earth because of, with instrument on board. We also have aircrafts that fly and also have instruments. And they measure so many things. They measure the amount of carbon. They measure the amount of water. All of these studies, as well as buoys in the ocean, they study the temperature of the ocean and so on. And all of this thing is collected, and scientists use all of the data using computer model to assess the state of health of the Earth and also the various components that will impact the quality of life. But for the most part, starting in the 1960s, we started to use satellite. We fly satellites, and we collaborate with other nations. NASA is not the only one that does that. We work with other space agencies. And in the future, we'll be working with the Australian Space Agency to collaborate on the study of Earth. And so you guys better start, you better start thinking about that, to carve yourself a place in our scientific environment to do something that's so great, the study of the Earth, and as well as the study of other things to serve humanity and to better the life for mankind. So this is, what we have, a number of, did we go over the satellite? Okay. This is a train of, we call it the A train, a number of satellites. They measure just about everything from the amount of carbon to so many things up in the air and give us some data, that we study for Earth observation purposes. So, and also, we definitely, all of this, the data coming from all of these satellites has to be communicated somehow, and that's where myself and my colleague here come into play, because without communication, all of these satellites will be pieces of junk up in space. The data is transmitted back to our ground stations, and then they are transmitted to the scientists where they are further evaluated. We use different kind of networks for that. In particular, I talked about it, the Near Earth network, where the satellite goes around and dump the data to these polar areas, and then the data goes, through ground connection to the the investigator to collect it and study it. We also use the space network to do that, and from up in space, we have visibility to everything that goes around Earth. So anything that all data collected around there, will be able to make it through to its proper destination. Next thing we study, guess what? The sun, heliophysics, the origin of all life around Earth. Without the sun, there is no Earth. And the sun impacts our life on Earth, drastically. And what do we study about the sun? We study the sun itself, and the sun, as you all know, is a giant ball of gas. It's about 1 million times the size of Earth. And what I mean is that within the sun, you can fit about 1 million Earths. And the sun is the mother of all of the planets in our solar system. What does it do? And with the composition of the sun, the same thing we talked about Earth, there is a core. And in the core, there is like a nuclear reactor taking place. The pressure and the heat over there, take the hydrogen, nuclei in here and transform them into helium. It takes 4 hydrogen nuclei and fuse them together to produce a single helium nucleus. And we know the helium weighs a little bit less than the hydrogen. So what happened to the rest of the mass of these 4 hydrogen nuclei? They are transformed into heat. And this heat propagates upward. And we have a radiative zone in here, and where you have so much heat, and that translates into, into the convection zone to create something similar to what happened on Earth, create a certain magnetic field and magnetic energy, And all of this causes a number of things to happen. This heat and these heated particles that come in from the sun, we define as the solar wind. These are highly charged particles that are constantly transmitted by the sun. In addition to this steady stream of particles, we also have a number of electromagnetic explosions that take place in here. One of them is the coronal mass ejection. Like a bubble of gas heating up and bubbling to the surface and expanding as it goes outward, and then boom, a massive electromagnetic explosion takes place, and and a lot of additional heavily charged particles come and propagate through space. But they are slow, they are heavy. They take a while to get to Earth, about 8 days. The other ones that are more dangerous are the solar flare. We talked about the sun being a ball of gas. So it's more fluid. The movement of things is not like the Earth, where the Earth is solid on the outside. So the electromagnetic field around the sun is different from the Earth. And around Earth, they are pretty defined, and they are also aligned. Around the sun, the electromagnetic field, they get wound up around in so many different directions. And sometimes they get mingled together. And when that happens, it creates a very intensive electromagnetic field, causing solar flares. These are like explosion, electromagnetic, kind of highly charged plasma or highly charged particle that are emitted into space. And they come to Earth, they can get to Earth within 8 minutes. They are very fast. These are the kind of photons that are highly charged, that are going through space. But what's good about our environment and our magnetosphere, it protects us. As these things, highly charged particles, come here to hit the Earth's environment, this electromagnetic field that around the Earth push them back. Not only that, they get diverted. When they hit the Earth, they start to slow down because of this what we call the Bow-Shock zone. And this is they are pushing against the electromagnetic field. At the same time, the electromagnetic field pushing them out, so they get diverted. And that's what protects us. If this did not exist, all of these highly charged particles would come to Earth, and they strip Earth from everything. Anything that fly, all of the molecules in the air and everything gets stripped out. And as you all know, you heard about the aurora borealis and the aurora australis. Do you know what the origin of the name of Australia come from? What does Australia mean? Southern light, terra australis, southern land. And that's what we have. As these things, these highly charged particles go around are captured by our electromagnetic field, they are taken to the poles, and as they enter the atmosphere, they interact with the nitrogen and the oxygen and the air, and they give us these beautiful lights. Oxygen can give us light like green and sometimes yellow and so on, while the nitrogen gives us the beautiful blue color. And it happens, on both sides of the planet. So I'm talking like about the sun as if the sun is a bad thing. No. This solar wind go to the edge of the solar system and protect us, because the sun is not the only star out there. There are plenty of stars everywhere, and all of them are transmitting similar highly charged particles. So our sun, send this solar wind and push against all of the interstellar wind that's coming, all of the bad things coming at us from outside. And so the sun is protecting its babies, while the babies are supposed to be grown up to protect themselves from mommy. So this is a very delicate balance. And look at the sun. The sun alone is 99.8 of the total mass of the solar system. That's a huge thing. That's a very big thing. All of the rest of the planets is just 0.2% of the rest of the mass. And and then we can talk about the planets. There are two different types of planets. the inner planet and the outer planets. And NASA and other space agencies do study the planets. Do we know why? Why do you think we study the other planets? What's going on? Why? Because we'd like to know, how our solar system was formed. In order to understand the total solar system, you need to see the various elements and components of the solar system. Go ahead. Bingo, that's another thing. Did life ever exist there? And if it did exist, what happened to it? And could what happened over there happen on Earth? And how can we protect ourselves? So all of these things are reasons why we study the other planets, to have a better understanding and better appreciation how to preserve life in here, and to see if life is possible in the future in other planets, potentially, as we have taken to the oceans and to the seas to discover and inhabit a new land, we probably want to go one day to inhabit other planets. So among the planets that we study, and although the moon is not a planet, but it's the closest heavenly body that's closer to Earth, and we try to study it. The beauty about the moon, it's a dead semi-planet. Nothing going on over there. At one time, it used to have volcanoes, so it was a little bit active, living. But about 100 million years, during the time of dinosaurs, volcanoes stopped. The moon became like a dead rock, empty, there is nothing to it. Recently, we discovered there's plenty of ice at the southern pole of the moon. But the good thing about the moon, because there is no water, no nothing, it has a good memory. Everything that has happened over 100 million years has been captured by the moon. It has captured the heartbeat of the solar system, and by going there, we can study what has happened over the past 100 million years. Because there is no rain, no nothing, no earthquake to change the topography or rain to cause runoff. So everything has been preserved. So it's a pristine place to study what has happened and the effect of the various cosmic phenomenon on our solar system. So we have a spacecraft called LRO, which is Lunar Reconnaissance Orbiter, has been flying around the moon for the past 10 years, giving us these kind of critical data. We also study Mars. Mars has been the planet the most studied. And presently, we have a number of vehicles and laboratories on the surface of Mars. You all know about JPL being the only entity that was able to land vehicles and rovers and landers on the surface of Mars. And they are presently going around studying the terrain, studying the molecules that exist over there to draw conclusion. Does water exist and so on? But in 2020, JPL will be sending another thing, another vehicle, another lander or rover to study whether life ever existed over there, to look at the element of life that around Mars. And we are looking forward to get these kind of results. Mars has always fascinated us. It's a red planet. It's similar in size to Earth. It's a little bit smaller. It's a little bit distant from the sun. What it has also, it has all of these components that are similar to Earth. The only thing it does not have is this electromagnetic field that I talked about. That bubble that protects Earth doesn't exist around Mars. So radiation can strip just about anything. All of the molecules that exist around the planet can be stripped by the solar wind and the space weather. We'd like to understand what happened. We know Mars at one time had active volcanoes. There is water. We discovered places where water once existed. Things that are carved in the rocks and the topography that indicate there were water streams and rivers potentially and lakes. So the 2020 mission will give us these kind of answer. We'll be looking at organic molecules. This is the basic component for life. So, in the next few years, we'll be answering so many good questions. Okay, if life never existed, can life be supported over there? Can Mars at one time in the sometime in the future, be re-energized? We can make it a little bit more active to sustain life in the future. It's not that far away from Earth, So it may be a good place to go to, as we move forward into our solar system. We also study these big ball of gas, the other big planets. Saturn was always of interest because we were fascinated by the rings and the moons around Saturn. And recently, we had a mission called the Cassini that involved a number of space agencies. They went to study the rings around the planets and studied the moons over there, studied the electromagnetic field. And after 20-plus years, we got them to go through the rings and make a plunge on the surface of the planets. We are trying to understand the nature of these gas balls. Jupiter is one of them. Saturn is one of them. Our understanding of these planets will help us to understand our own Earth, life, and the origin of this solar system. And this is so critical to our evolution. And so I talked about Voyager. It's a major accomplishment. People just talk about the landing on the moon as a major accomplishment 50 years ago. Having a spacecraft crisscrossing the heavens for the past 40 years and going beyond the influence of our sun to go into the interstellar area is a major accomplishment. A spacecraft that survived all of the elements and got speed as it went around using the planets to push it forward, to make it into the interstellar areas and still be able to transmit data. And that's a miracle of our ingenuity, what we are capable of. This spacecraft has 100 watts, like one of these light bulbs, transmitting data from 20 billion kilometers. That's not your next door city or whatever. That's pretty far away. And that's why we need the antennas that exist in Tinbimbila. Because these spacecraft, we can only see them from the southern hemisphere, in particular from the station down here. Ed Cruzen is the station director. And he's doing us a big favor, helping NASA and the scientific community keep contact with these spacecraft, helping Susie with her 2 missions, trying to discover what's out there beyond the solar system, looking at the interstellar radiation, the composition, and so on. These spacecraft are going to keep on going until they stop. And as long as we have the antenna down here, we are going to still support them. So this is what I'm talking about. Just imagine 20 billion kilometers. By the way, the data here is wrong. This was a few years back. We did not change the chart. Now we are at 13.4 billion miles, or about 20 billion kilometers. That's a long, long way. It took 40 years, going at 50,000 miles per hour to get here. This is a major accomplishment, similar to the landing on the moon. And this is what I talked about. This is the kind of antenna. As the signal gets weaker because the spacecraft gets further and further in space, we need these big antennas. These are giant ears that are so directed in a very narrow way to that spacecraft to pick up the signal. And in here, we have super duper electronics. The power and the ingenuity of our engineers to come up with the kind of technology that will allow us to pick up very weak signals, despite the noise coming from everywhere. Anything that's happening around us can interfere with that signal. But yet we do it. And thanks to, in large part, to the ingenuity we have at our JPL center, as well as the collaboration with the CSIRO folks who are providing us with that tremendous service. You guys, please, if you haven't been to the Tin Bin Villa, go and see these antennas. They are our Eiffel Towers. Even better, they are doing something, in the service of humanity, not like sitting, not doing anything, just collecting tourist money. And then from there, we move into the universe. Boy, the universe is so huge. How huge is it? Very huge. Why do we study it? We try to study the origin of our life here on Earth. What's happened? How did we come about? Our place in this universe. How relevant are we to the rest of the universe? Are there life elsewhere? Are there other planets in the universe similar to our planet? You can see here, this is our sun. These are our planet. What's in red here is Earth. This whole thing, the solar system, is just one point in a big galaxy. We call it the Milky Way. We are 26 million light years from the center of this galaxy. This galaxy is about 100 million light years. What's a light year? It's a distance that a light travels within a year. Light travels, about 186 miles per second. Look what a light year is 5 trillion, 800 billion, whatever miles. Woo, that's pretty huge, isn't it? That's a big distance. And just to show you the sheer size of the universe. So when you see people pretending that they are bigger than life, look at this. Put things into perspective. Our entire solar system is nothing but a single point in a much larger universe. No one is bigger than life. Life is much bigger than we are. And when you look at our galaxy, it has 100 billion stars, like Earth. Just imagine that, 100 billion stars, that each star has so many planets around it like we have. And when you look at the, possibility of life elsewhere, we sent a spacecraft called Kepler. Started to look at our immediate neighborhood. And as of January 2019, in a small corner of the Earth, we discovered, we have confirmed the existence of about 4,000 planets like Earth, where life could possibly exist. However, they are like light years away from us. So how do we make contact? How relevant are we to them, and how relevant are they to us? This is the question that I'm hoping all of you would answer in the future. So if you look at not just our immediate neighborhood in the universe, our neighborhood is 20 light years across. Our Milky Way, it talks about our spiral things. Where are we located? This is our immediate neighborhood. And when you take this neighborhood and look at the whole neighborhood that we are talking about, it's just that small place in a much larger universe. There are about 2 trillion galaxies similar to our Milky Way. And each galaxy has 100 billion of stars. This is an infinite number. There's a probability of other planets. In our immediate neighborhood, we found 4,000 planets similar to Earth. In much larger things, there are millions, yet billions of planets similar to ours. And if they have the right condition for life that we have on Earth, they must have life on them. And there is no reason that that's not the case. And at the heart of most galaxies, there is a black hole, and I will talk about that. But if you are to count the number of stars up in space, there are more stars up in space than number of grain of sand on Earth. If you collect all of the sand on Earth, there are more stars than the number of grains of sand on Earth. This is much larger than anything. So what does it mean to us? We'd like to understand it. Would like, if there is life elsewhere, would like to make contact. That's why we need to evolve our technology, our capabilities, to reach out and see what's out there. You know, I talked about the black hole. Do you all know what's a black hole? Okay, so a black hole is something that sucks up, you know, it has huge gravity, strong gravity. It sucks in energy. It does not send it out. It pulls it in. Even the light cannot escape from it, you know. And at the heart of each galaxy, there is a huge one like this that swallows things, you know. We don't understand what's happening inside of them. This is the kind of physics that I'm hoping many of you will pursue, so will help us understand. And we didn't know about them. We suspected they existed. Einstein talked about them. You all heard about Einstein. Yeah, but we never demonstrated that until recently, where we were able to measure it and to feel it, to see it, by the way the light bent around them. So what am I talking about here? This is our universe. Our universe is not sitting still, keeps on expanding. You know, it's not contracted. Well, so, and it's not only expanding, it's expanding, it's going larger and larger at an accelerated rate. And we estimated that the age of this universe, 13.8 billion years. Some people put the age even much bigger than that the universe has expanded and collapsed so many times. But these are all theories. No one can prove that. So what enters into play here is the makeup of the universe. You know, what we see and the planets and those things that emit light or reflect light is only about 5% of the total universe. 26% is, you know, or 95% altogether is something that we cannot see. We know it's there. Some of it is dark matters, and some is dark energy. The dark matter is the thing that holds things together. The dark energy is what's pushing the world, you know, to keep it, continue to expand. So what's going to happen in the future? We don't know. And when we talk about the future, we are talking millions and billions of years away. Some people are talking about that the world could rip apart. Some people are saying, okay, we are going to grow up to a certain size and stop there. And some people are going to say that everything is going to collapse and going to implode back. We don't know. These answers, we try you know, these questions, we try to answer them ourselves, but we are no close to finding the answers. We are counting on you, on your generation, to find these answers. In the process of doing all of this, doing all of these studies, we keep on sending spacecraft, whether around Earth, around the sun, around the planets, to keep on looking for clues and answers. Space has offered a good domain, and you know, for technology evolution, technology that we can take and then apply in our day-to-day life. Your tennis shoes, your radios, your smartphone, that all comes from space-related technology. So space has a place for all of you. And I'm hoping that you'll all participate in our exploration and come along on our journey to discover the unknown. So follow our exploration. You can go to our website and get a lot more information. And I'm now open for questions if you have any. And I may have a NASA pin and NASA sticker for those who ask questions. Those who do not ask questions, they are not getting anything. Okay. Oh, you have to be smart. You have to have something that no one else has. You have to be determined, you know, and you have to be willing to work hard. Then we'll put you through a rigorous training and prepare you to live in zero gravity environment, to do the functions that you are capable of doing. But it's not impossible. We graduate, astronaut on a regular basis, and I'm hoping in the future the Australian Space Agency will have a similar program. Hopefully by the time you are old enough to enter into this field, the Australian Space Agency will have such training capability. Okay. Yeah.
How long does it take for a signal from the Voyagers to reach Earth?
About 22 hours. Am I correct?
Yeah, a little over 20 hours.
20 hours. Yeah. Okay. She's going to keep track of who's asking questions. She's going to give you pins at the end. Okay? Oh, it's the best place to be at. It's where dreams can come true. NASA has been the ideal place for me. I grew up in Lebanon, in the mountains of Lebanon, among the cedar trees. And what got my attention to NASA is the moon landing, which we are going to celebrate the 50th anniversary. I'm not telling you my age. So 50 years ago, I was so impressed by NASA and our ability to put people on the moon. I was the kind of dreamer. I had always a big imagination. So NASA was a natural place for me to go, to really make my dreams come true. Okay? We can, by the way light behave around it, okay? Because they have the kind of gravitational forces. As the light goes by them, they affect the path of the light. So the light looks like curved, And that's when we determine there are forces that we call, black holes or something else. And you depend on their behavior. Is that okay? But this is a good question. I'm impressed. How about you? Does every planet? Now, our planet has a core, that's a very active core. Mars, it has a core, but it's a dead core. At one time, it's possible that it was a little bit more active, but everything has a core. Some of them are living core, like very active. Some are dead, like a dead rock. Okay. How about you? Depends where in space, If you are, I'm trying to answer your question, what do you mean by that? Well, you enter into the laws of relativity where time becomes function of your speed. If you are going beyond the speed of light, then your time becomes kind of measured differently. But if I'm to understand from you, probably not, your question not related to relativity, related, for example, if you are on Mars, like Mars takes a little bit longer to go around the sun. So the Martian year is by far different from the Earth year. The Martian day is different than the day over here. It's a little bit longer over there, very little bit. Is that that's what you're looking for? Okay. Okay. There are so many questions. I'm trying to keep track because I don't want to miss this side of the room. And please leave some time for other people to ask questions.
How did you find out, what's outside of the solar system, like the Milky Way? How did you find out what's there?
Oh, we send big, huge telescope. We have something we call the Hubble. And we have the Hershey telescope that the European Space Agency deployed. Between these telescopes, we can see deep into space and deep into the universe. And good news for all of you. In 2 to 3 years, we are going to deploy a much better and much bigger telescope. Has 10 times the power. We can go back in time and see the origin of the universe, back one time when the universe started. This is the James Webb telescope. It's a huge, stack of mirrors that's supposed to collect signals and lights from deep space and convert them into something that we can understand. That will be flying in about 2 years. So we use telescopes, but we put them away from Earth because on Earth there's too much noise, so much pollution, light pollution and other things that prevent us from seeing things sometimes. When you go into space, you don't have any of that, so you have a clearer view of what's out there. Okay, I'm going to take a couple more questions from here, then I'm going to move to the other side. Oh, but, yeah.
Have you found any source of any living things in another solar system?
Believe me, had we found something like this, we would be celebrating. You will be reading about it in the newspaper. What we are saying is that the possibility of something like that is extremely, it's extremely possible. The probability is extremely high. We don't know where. We are looking everywhere and try to detect any sign of life. As soon as we find it, you'll be the first to know. How about that? Okay.
How do you measure the mass of planets? You don't know what they're made out of?
No, we have to look at, at what they are made out. The composition of the planets. Are they empty? Are they hollow? Are they gas? We measure a lot of things. We have instruments. We look at the sound waves that, we do something like this, we study the sound propagation to understand the characteristic of that planet. We also look at the electromagnetic signals that are coming out of this planet, the makeup, because every element does radiate. And based on the radiation, what frequencies, we'll know the composition. Then we look at the size, and we come up with an estimate. And very often we are close. We are not completely accurate, but we are close to the real thing.
Do you know how many reusable rockets NASA has?
I'm not going to tell you. Well, reusable rockets, do we know the answer? No, but we retired the space shuttle. So everything we use, the only thing that we have is the SLS. We are building that to be reusable. We also have a number of launch vehicles that have reusable element in them. And the commercial entities like SpaceX and others also have some reusable things. We stopped counting after number 1. Okay. Yeah, the blue. Okay. No, they suck in because they have so much gravitational force, Even an entire star will collapse. The gravitational force is so strong. The star, these huge things, start to collapse until it becomes so small. That's what we call, singularity. As this entire star, the mass of this entire star collapses to a single point, And as it sucks it in, it make it like a spaghetti-like, And all of these things are theory, based on, scientific data. We have not seen that thing happening, okay? But this is more theoretical, okay? Excuse me? We are going to Mars to establish a permanent presence on Mars. We are developing the technology that will allow us to live there for an extended period of time. So this is a possibility. Mankind can accomplish so many things if we set our mind to it. If you are only bounded by the bounds of your imagination and also your capability. We have the technology that will allow us to do that. We are going to demonstrate that pretty soon with the Artemis program around the moon. We are going to demonstrate the technology and prove that we can generate the energy and reuse all of the volatiles around the moon to sustain life and to produce the kind of fuel that will allow us to travel into deep space. Oh, we have looked at all of the planets. NASA is the only agency that has explored all of the planets, including Pluto. We have a spacecraft called New Horizon that recently went by Pluto and now is close to the asteroid belt, looking at the composition of these things and sending data about them. I'm going to take this one and this, and then I have to move to the other side. I can be on Earth in Spain today and melt. The temperature over there is so high. Definitely the heat from the sun and is pretty tremendous. You are talking The corona of the sun, you are talking 10,000 degrees, very, very hot. So if you get to close, sometime in very hot days, you can feel it. Your skin burns. What protects us is the atmosphere around us, protects us from the radiation from the sun. You remove that, we won't last more than a few hours. Now, you come closer, you will not last more than minutes. You come closer, you won't last at all. We have a spacecraft now called Parker Probe. It's going to attempt to get as close to the sun, as possible. We launched it recently, and we should get some data pretty soon. This one, and I'm going to go down there. Okay. Yeah, then definitely. Let me answer the first question first, the second question first. Yeah, the solar wind does impact everything in space, impact our astronauts. That's why we try to harden everything to condition them such that radiation does not impact them. The technology that enters into the makeup of the telescope is hardened that can withstand certain level of radiation. As to the question of Voyager, I'm going to ask the Voyager project manager to answer that question. Yeah. What kind of data do you get from the Voyager?
What kind of data? So we get.
5 minutes, because you've got to get out to Tiffany.
Okay.
So what Voyager is measuring is what's out in interstellar space. So we measure charged particles, we measure the direction they're coming from, the energy level they're coming from. It's a bit like a weather satellite. We're not taking pictures of anything because it's very dark there, but we are sensing the environment that we're flying through.
Also electromagnetic field, that's always something we always look at.
Yeah.
Yeah. Okay, this side now. We only have a few minutes, so I would like, if you have a good question, lay it on me. Yeah. Yeah, we are going to create the habitat that you can live in. Until we can create this environment where oxygen can flow freely, we are going to wear suits that, protective suits, and live within our suits, and then move into the habitat. How are we going to create, to find, produce oxygen? We are going to take the water and break it down to oxygen and hydrogen. We are going to use it to breathe, and also as well as they generate liquid oxygen and liquid hydrogen to power up our vehicle. Okay? Thank you. Because it does not radiate light. It sucks in energy. So that's why we call it anything that does not radiate, takes in, we call it black hole. Because we don't see anything in it. Sky, the entire sky is dark. Unless there is light emanating or radiating or reflected over there, you cannot see anything. Okay? That's why it's so dark over there. Does it answer your question? Okay. Yeah. I wish I know. We've never sent anyone through it to know what's on the other side. It's only, all we can estimate is just, theories, but nothing has been proven, and there is no way to prove it. There is no way, unless you can send a probe in there to see what's going on, and they will not survive the journey. Okay? Few days to when we are going to go to the moon, we have the Artemis program. We expect to land on the moon by 2024. We are going to test our technology, evolve the capabilities, and so on. Hopefully March in the 2030s. Hopefully you'll be the astronaut to go there. I'll volunteer you. How about that? How about you?
If there's a weak core, is there anywhere that it can recharge?
That's something it's worth investigating. For example, Mars, at one time it was active. It has an electromagnetic field because we found a trace of it. So what happened to it? How can we restart this engine to start, to develop this electromagnetic field such that we can have a living environment? Because it has all of the other components for living. And there is so much ice over there, we can produce oxygen and we can produce other things over there. Okay, how about, yeah.
If there are so many stars in the sky, why are, like, at the night, why isn't the entire sky just full of stars? Why is there space?
Oh, okay. No, there is so much star, but the vacuum is much bigger. The universe is much bigger. You know, despite the fact we have so many stars, there's still plenty of emptiness around there. There is also the dark energy and all kind of things that exist. And many of the stars we don't see. Their light do not get or have not gotten to us. They are so far away. The light is still traveling and hasn't gotten here. Okay. 5 more minutes. Oh, all of the planets all of the other stars are like the sun. They are ball of gas, you know, where at the core they are, you know, there is like nuclear fusion, nuclear reactor producing so much energy. What we are looking for is our planets, inhabitable places around them, to see whether if there is life over there or not. Okay.
Is it possible for a star to orbit another star?
For stars to collide?
No, like for a star to orbit another.
I haven't seen it yet, but there is still a possibility. Also, you look at Jupiter. It's a ball of gas. What's going to take for this ball of gas to become so active, to become a star itself? I don't know. But it's going to be a very small star. But from a possibility, yeah, why not? You know, okay? Because it's a small thing, you know. And Mickey did not, you know, feed it enough to grow to become a big planet. You know, Pluto. No, for me, it has all of the elements for it to be called a planet, but some people want to call it a dwarf planet, you know. Huh? Oh, you're talking about speed? Okay, we are talking about potentially, well, in order to break through the Earth's environment, the low Earth's environment, you need about 22,000 miles per hour. You know, that's so you need, you know, depending on what you are carrying, you need the kind of thrust power to take you there. The next SLS, our space launch system, will have probably about 11 million pounds of thrust power. That's a lot of things to allow you to take about 45 tons of payload into deep space. They are pressuring me. I cannot get tired of you all. You know, I did not get to hear, you know, but, you know, I know all of you have plenty of questions, and I'm so happy about that. That gives me a good feeling about the future and about the future of the Australian Space Agency. Look forward to working for this lady over there. Really, you know, space is the next domain. There are plenty of commercial opportunities. NASA is working very hard, along with other agencies, to commercialize space, to create other opportunities. So what you saw in the movies, be that Star Trek or Star Wars, is going to become a reality. It's life copying, science fiction. It's going to happen. So be there and be ready for it. Thank you all.
Yes, so Badri has another audience to get to, so he's got to get in a car and get out to Tidbinbilla. So look, they were great questions, and just keep them coming. The website, there's a lot of information on the NASA website, and keep in touch. And if you've got questions, fire them to Questacon, and we'll find a way of getting some answers to you.
If you have any questions, this is our website. Send them to me, you know, and Barbara will answer them. Okay, and the stickers also have our, you know. Okay, no pins? How about all of those? Do you have enough pins? Too many questions. You didn't expect that. That's very encouraging. I love that. You know.
So look.
You see, you are going to have the cadre for the future. You know, over there. Best of luck to all of you.
Okay,
and
so look, one last time, let's thank Badri. Thank you. I've left you.